Don't forget to subscribe and ring that bell.
Here we go. Some tips and tricks for the AP Calculus AB exam that you should know. And maybe you know them, you should probably remember them. 95% of the exam will test you on equation of a line, derivatives, and shocking, integrals. The other 5% might be limits, slope fields, intermediate value theorem, and other poop like that. So, first of all, the equation of a line tangent. No, do not use slope intercept form. That was when we were in Algebra 1 all those years ago. Instead, use point slope. This is great for a variety of reasons, but mainly all you need is a coordinate, an x value, a y value, and then you need the slope. And guess what, kids? Slope is basically just my derivative. Yay. They will give you a coordinate, which we're going to put in x1 and y1. However, if they only give you the x coordinate, don't forget, we can put that right into the original equation, and that will give us the y we're going to need. Right? And my slope, well, that's just what I get when I get the derivative of my function at the value x1 from above. So, Visca, what if all my multiple choice answers are y equals mx plus b? Do I still use this? Abso-freaking-lutely, definitely. How come? Because number one, it's easy. And number two, all I have to do is subtract y1 from both sides. Excuse me, add y1 to both sides. This goes bye-bye. And now we have y equals. If you need to, distribute this and combine like terms. Derivatives, derivatives, derivatives. We have the power rule. We have the chain rule. We have the product rule. We have my favorite all-time and so underappreciated quotient rule. We need to know the derivatives of E and natural log. Oh, by the way, those pesky trig rules for derivatives. Did you ever notice that anytime a trig function begins with C, the result or the derivative is negative? You're probably not going to need to know cosecant and cotangent. They hardly ever pop up on the exam. And if they do, it's probably going to be where you get to use a calculator. What about log base and variables in the exponents? Boom, not on the exam. So let's dive into the relationship between derivatives and integrals just a little. First of all, we have our original function, which we call f of x. The derivative is f prime of x, and the second derivative is f double prime of x. They are all one derivative away from each other, which means if you're starting with f of x, you need to take two derivatives to get to the second derivative. No, no. If they ask you for the second derivative and they give you the first, do not take two derivatives just because your brain is thinking second derivative. The second derivative is only one derivative away from the first. Do not just do two derivatives because they mention second derivative. Know where you're starting. If you're starting with the original function, sure, it's two derivatives. But if they give you the first derivative, don't you dare take two derivatives to get to the second derivative. Which, oh, by the way, integrals are just going backward. From second derivative to first, one integral. From first derivative back to original equation, one integral. And let's look at this in the terms of units or words. They're not always going to say find f prime. Sometimes they might give you gallons per minute. That is a rate, children. And if they want gallons per minute, or gallons per minute squared, that means you take the derivative because they're asking you to find the second derivative from the first derivative. Rule of thumb, if they just give you the unit, for example, gallons, you have the original equation. If they give you a rate, your unit per time, like maybe gallons per minute, you now have the first derivative. If they give you units per 2 times, minute per minute or minute squared, that's the second derivative. Sometimes your unit, let's call it, I don't know, inches, might not be per second. Sometimes they say per degree Celsius, or vice versa. That's really rare. But I think you know that this is a rate. This would be the original equation, and inches per degree Celsius squared would be the second derivative. So what can I do with derivatives? My goodness gracious. The rate of change, or the slope at one point. Extreme values, finding mins and maxes. Let's not forget, those only happen at critical points, where the first derivative is equal to 0. The rate of some unit, if I have gallons and I want gallons per minute, that's a derivative. Or if I have a rate, gallons per minute, and they want the rate of gallons per minute, or the rate of that rate, we're taking the derivative. By the way, if my first derivative is positive, my function or graph is increasing. That means I have a positive slope. If my first derivative is negative, that means my function is decreasing. That means I have a negative slope, downward, upward, and onward. What about integrals? Well, integrals are area under the curve. Sometimes they give you two curves and you got to find the area between the curves. If that's the case, it's always the top curve minus the bottom curve. And if you are going to integrate them, please put them in parentheses because you are subtracting the entire function that represents the bottom curve. There are times, though, kids, where we have a table. Oh, I love tables. And we got to do the area under the curve using the LRAM. Left, Riemann's approximation method, rectangular, left rectangular, something with a Riemann sum with the left side. Left rectangular approximation method. Oh, thank God. Or you got to use the RRAM or the MRAM, which is middle. Okay, those are easy. Or the trapezoid rule, which I personally love as well. Oh, we don't get to use the Simpsons rule. Oh, I wish we did. I love it so much. But we'll stop with the trapezoid rule as far as area under the curve. Don't forget, if we're integrating a function like the derivative, integrating brings us right back to the original equation. If we don't have bounds, notice there are no bounds here. I need to have a plus c. Okay, and I cannot find out what that c is unless they give me an initial condition. Maybe they say when x is 2, y is 7. Then I could plug those into my original equation and solve for my c. If they do give us bounds, the rate that I integrate brings me back to the original equation with the upper bound in it minus the lower bound in it. I cannot tell you the number of times, I guarantee at some point on your test, they will give you the value of an integral with bounds in it. They will give you the value of the original equation, if this is a rate, for one of the bounds, and expect you to find this one. You simply set this up. Okay? In other words, the way they typically ask it is, if the integral of f prime, some rate, is 7, and f of 2 is 8, what's f of 1? Basically what you can do is put your upper bound here, your lower bound here, Okay, actually, they might not even give you this. Okay, they say f of 2 is 8, find f of 1 if the integral, blah, and here's the integral, whatever. Just throw your upper bound and lower bound. Put this in the calculator, hit enter, you'll get a number. Maybe it's 7. This should equal f of 2, which is 8, minus f of 1. Well, 8 minus 1 is 7. So f of 1 is 7. It's so freaking simple. Boom. Whenever we got to total up units from a given rate, like if I have gallons per minute and they just want me to find out how many gallons, that's an integral, okay? Whenever we need volume, we need to integrate the area. They say, okay, here's a graph, here's one line, here's another line, and this region right here is a bunch of triangles stacked upon each other. Find the volume. Well, the area of a triangle is 1/2 base times height. Okay? This is what we're going to integrate. Typically, it's like squares, which is side squared, and my function equals my side, but don't forget I got to square it. Whatever the area equation is, we integrate it for volume. Sometimes they rotate around a point, typically the x-axis. If we rotate one function around the x-axis, that gives us a disk, which is a circle, which is pi r squared. The function is your radius, okay? But sometimes they have two functions. And now look, I have a washer, which means I want all this, but I got to subtract the blue from it. It's the bigger curve squared minus the smaller curve squared. Don't forget they're circles, so you still need that pi on the outside. And last but not least, the second derivative is concavity. If my second derivative is positive, I got a smiley face or it's concave up. If my second derivative is negative, it's a sad face and concave down. Don't forget, you can only change from sad face to happy face or happy face to sad face at an inflection point where the second derivative is equal to 0. Here are some basics that I kind of want to wrap this whole thing up with. First of all, for the love of God, if they give you any information like this, they're really giving you a coordinate, -4, 7, okay? Just run with it. What about average rate of change versus average or average value? The average rate of change will, well, first of all, it's just changing y over changing x. It's the slope between 2 points, people. All right? They'll say 95% of the time, average rate of change. The only times I find that they don't use the phrase rate of change is when they tell you, hey, estimate f prime of 7, and they give you a table. They don't even give you an equation. You can't take the derivative of it. And 7's not on there. 7 would happen to fall right in between 6 and 8. So we're going to use these two coordinates in here to estimate. We can't find it exactly. That's average rate of change. When they say average value, okay, and they've been getting tricky. They don't say value a lot of times. They just say find the average. You're integrating a function from a lower bound to an upper bound and multiplying it times 1 over the difference of the upper bound and the lower bound. Okay? For example, they may give you a rate of people entering the store per hour, right? They say f of x is that people entering the store for an hour, and they say find the average of the rate of people entering. Kids get confused because they see this right here, average rate. And they're like, oh, it must be this. No. If they say find the average rate of people entering the store between time 0 hours and time 5 hours, these are my upper and lower bounds, my A and B value. Do not do this, okay? They're saying find the average value of the rate of people because they give you the rates of people. They can be tricky with that. All right, graphs and tables and charts. Oh my. If they say this is the graph of f prime, for the love of God, I got to stop saying that, okay? Label the y-axis as f prime, damn it. So here, I normally always just write y next to the y equals f prime. That tells me that any coordinate on this graph, any y value of that coordinate, is the slope of the original equation f. So if I'm above the x-axis, these are all positives. Okay? If I'm below the x-axis, all these y values are negative. So for these locations, my original function f is going to have a slope that's positive. And down here, my original function f is going to have a slope that's negative. And I don't know if I said this or not earlier, but you have f. F prime is the slope of f, and f double prime is the concavity of f, the original. But you see how this is only one derivative away? And isn't derivative slope? So the slope of f prime is the second derivative. So if I look where I have a positive slope here, starting from the bottom, going up, that's a positive slope. So my second derivative is positive because that's the slope of the first derivative. Right here is a slope of 0. So my second derivative is 0 there. That might be an inflection point. My slope of my graph of f prime is all negative here. So I have a negative second derivative. Again, a slope of 0 at the bottom and a positive slope of the graph of f prime. If that confuses you, rewind it, watch it again. I guarantee that's going to come into play at least once. The mean value theorem. All that means is if I have a function that's differentiable everywhere, if it's differentiable everywhere, it's continuous everywhere, that the change in y over change in x over the interval that they give us has to equal the derivative at some one point c, where c is in between our interval. Okay? They might say function between 2 and 7. That means this is x1 and this is x2. Not only are they going here, and then I'm going to use them to find these values in the original function, then my c value is between there. That's it. Implicit differentiation versus related rates. Oh, goodness gracious, guys. Implicit differentiation is they just give you an equation with x's and y's. You take the derivative of x just as it is, the derivative of y the same way as x, except every time you take the derivative of a y, you need to write dy dx next to it. You're multiplying it. This is the product rule. First times the derivative of the second. The derivative of y is 1 dy dx plus the second, first times the derivative of the second, plus the second, which is y, times the derivative of the first. The derivative of 2x is just 2. And don't forget, I also got to take the derivative of my constant, which is 0. Related rates is almost the same thing, except we might have a balloon that's a circle that's inflating. The area of this balloon, which I guess would be a circle. Balloon's 3 dB volume. But anyways, pi r squared, constant. The derivative of r squared is 2r. Anytime I take the derivative of a variable, I got to put dr dt or r prime there. A better example, because it's for every variable, a better example is the Pythagorean theorem. If I take the derivative of this, all of these are 2a, 2b, and 2c, but for every one, I got to put like an a prime or dA dt, or a b prime dB dt. Or if I'm taking the derivative of the c, it's got to be c prime or dc dt. Related rates. Do it. Do it. Separable differential equations. I love doing these. All we have to do here before we integrate both sides is get my y and dy alone on one side, and then I'm going to get my dx and my x's alone on the other side. Okay, so I'm going to multiply this side times 1 over y, boom, boom. So I got 1 over y here as well. I'm going to multiply the side on the left by dx, boom, boom, dx. So I've got 1 over y dy equals 3x squared dx. Now I just go and integrate both sides, and I just do so much better in this problem because I can integrate and we kill this problem. Look it, kids, don't get nervous. Let me point something out here. Okay, let me point something out. Multiple choice is worth a total of 54 points. I think each multiple choice question is like 1.215. I forget what it is, but it's a decimal slightly bigger than 1 to get to 54 points. Why do they do that? Because the free response questions, 9 of them, there's 6 of them, they're 9 points each. That's also 54 points. So they wanted multiple choice and free response to count for the same amount. All right? That's why each multiple choice question is like 1.2 something. But what I want you to pay closer attention to is this chart right down here. Out of the total 108 points, when I add my multiple choice and free response question, that's the highest you can get. If you can get in between 64 and 108, and this was like from a couple years ago, but it doesn't really change that much. If you only got 64 out of 108 points, that's 60%. Bing, bang, boom. That's a 5, kids. That's a 5. If you get from 50 to 63 points, that's a 4. Do you know what 50 out of 108 is? 47%. A 4 is 47%. I mean, I can't, guys, I can't. 38 to 51. 38 out of 108 is 35%. That's a 3. Oh my God, kids, I ain't even going to go over a 2 and a 1. I'm not even going to go over it. Okay? It is very highly likely, in fact, common, that you can get a 4 or 5 easy. In fact, I think at least 60% out of all kids score in this range. And there are, 330,000 kids across this country or something that take this exam. You got this. So, remember, kids, you're going to do fabulous. Knock it out of the park. Reply, I am genuinely interested to know how all you guys do on this exam when you take it. When you get your score, find me, find one of my videos, find this video, throw a comment on there and be like, hey, Visca, I did this. Maybe I got a 3, I'm going to do better, I'm going to retake it. Maybe, Visca, I got that 4. Visca, I got that 5. I want to know. You got this. So just relax.
Don't forget to subscribe and ring that bell.